Before starting, I would like to say thank you to the organizing committee for the invitation to this conference. This presentation is focused on how oyster farming can contribute to climate change mitigation, acting as blue carbon ecosystem. The outline of what we are going to speak about is divided in three main points, explaining why oyster farming can be considered as a sustainable practice, what is a blue carbon ecosystem, and how oyster can be considered one of them. Let me start. Based on the last report issued by FAO in 2022, aquaculture development has exponentially increased in the last decades, reaching in 2020 about the same production values of fish captures. This could be due, from one side, to the progressively unsustainable exploitation of fisheries, and from the other side, because aquaculture is becoming a source of income for many countries, especially among the middle income countries. Within aquaculture production, mollusks that are for the major part bivalves have raised 20% of the overall production and are predicted to increase to about 45% in 2050. At worldwide level, the four main species farmed are the capped oyster, manila clams, scallops, and mussels. As you can see, oysters are the most produced and consumed in the world, with around 5.5 million tons per year. The habit to consume oysters as raw product is diffused only in few developed countries, such as Italy, for example, where they are very expensive. They can arrive up to 2-3 euro per piece and considered the luxury food par excellence. Otherwise, all around the world, especially in China, that is the main producer, oysters are a sort of common food, processed in different way from soup to sauce. Farming methods fall generally into two categories, on bottom and off bottom, chosen depending on several different environmental and sea conditions. On-bottom systems simply means that oysters are growing on the seafloor, the closest to growing like wild oyster. Whereas in the off-bottom systems, oysters are growing without touching the bottom. In its turn, off-bottom system can be furtherly divided in a surface floating, where culture gear floats on the water surface, and suspended cultures, where oysters are typically suspended in cassettes or cage from a buoy and hang underwater. It goes without saying that there isn't a best or worst method. All of them show advantages and disadvantages. The choice depends on the condition of environment, for example, temperature or latitude and sea. But all of them have the final aim to obtain commercial sized oyster that usually are animal of about 70, 100 grams, obtained in 1836 months. Based on the life cycle assessment framework, it has been possible to calculate the carbon footprint of different systems of oyster farming. As you know, LCA is a standardized method which permits to include all inputs in terms of material used, fuels, energy, kind of both, necessary to produce a unit of product, usually, or in this case, 1 kilograms of fresh oyster, and estimated all the emission related to the production. Oyster production and processing usually consist in some phases, that is, a seed production or seed procurement, pre-fattening and fattening, harvesting, selection, packaging, and, where done, post-harvest processing. It has been estimated for oyster farming, even though there is a few paper regarding. It has been estimated for oyster farming For example, using a floating system in China, a carbon footprint of about 70 grams of CO2 equivalent per kilograms of fresh product. In another publication, it is reported in Washington about 170 grams of CO2 emission, and the last two are related to Italian cases in a range from 300 to 1,200 kilograms of CO2 equivalent using an offshore long-line plant far from the coastline, so needing of a great amount of fuel for boats. Moreover, you can consider in evaluating the fact that in Italy the environmental footprint is higher than in other countries, the fact that in Italy the production is by now very, very low, not more than 20 tons per year at all. That means that the impact per kilograms is unavoidably high. So we can consider at the end the more reliable data, the Chinese one. Understand if all the estimated values are high or low, they could be compared with other food. Even in the case of carbon footprint in Italy, that is very high with respect to the other, the China case, the values is anyway comparable to vegetal product and so very, very far from the other protein source, even farmed fish. So we can conclude surely that oyster farming is a sustainable and low impact production. Having said all of that, oyster, as well as other bivalves, may be considered one of the few types, maybe the unique, of a food that match at the same time several SDGs. For example, they contribute to regional poverty because they are a source, as we can said before, of income for million people. Obviously, they contribute to that of hunger, being an important protein supplier for many countries, not only as simply food, but also as high quality food from nutritional point of view. It is known that bivalves are a source of high quality fat acids, vitamins, and antioxidant substances. Moreover, they push responsible consumption and production because bivalves farming is a sustainable practice that can reduce the pressure on fisheries. They also contribute to preserving life below water because they don't need of feed or drugs or additives during farming and follow the natural life cycle of animals, being a form of not intensive aquaculture. The innovative aspect we discussed here is that they also can help in action against climate change, acting as a blue carbon ecosystem. But what is a blue carbon ecosystem? Based on the definition of IPCC, blue ecosystem are all biological driven carbon fluxes and storage in marine systems that are amenable to management. Coastal blue carbon refers to the carbon taken from atmospheric CO2 and fixed by aquatic vegetation, such as salt marsh, mangrove, and seagrass. The blue carbon is analogous to the green carbon that is fixed by terrestrial ecosystem, but it is of growing interest about the scientific among the scientific communities and policymakers because it has been estimated that the carbon sequestration capacity per unit area of coastal blue carbon is far greater than that of the terrestrial carbon pool. Restoring, conserving, and enhancing blue carbon will increase carbon sinks and produce carbon credit, which could be traded on the carbon market. Recently, also shellfish farming has been included as another possible blue carbon ecosystem because shellfish can act as a carbon sink. Bring us quickly to the third point of the presentation, that is how oyster can contribute to this and consequently can contribute to reduce emission and give help in climate change mitigation. In fact, oyster farming can be considered a long-term carbon sink. The concept is based on the fact that all bivalves capture two molecules of bicarbonate during their growth for the biocalcification process that leads to the shell formation and growth. Based on the chemical reaction of the two carbon dioxide molecules captured, one precipitates in shell and the other is emitted again in the marine environment. This issue that has been very controversial for years in literature and in the scientific discussion because, in absence of the surrounding environment at individual level, bioclassification seems to be, and really it is, a net source of CO2. But in an ecosystemic perspective, the surrounding marine environment cannot be neglected, and the molecules of CO2 emitted by the reaction of calcification never reaches the atmosphere because it is captured by autotrophic organisms in the surrounding of oysters. Moreover, even only considering the chemical balancing rather than a net source, it is a sort of net recycling where CO2 goes back where it came from. The final result is that one of the two molecules is permanently withdrawn or taken out from the environment where, when shellfish are harvested and the other come back to the sea. All contribution to CO2 emissions by oyster metabolism and respiration that in an individual view represent a net source, in an ecosystem view is negligible because submitted to the same fate of the molecule emitted by calcification, that is, to be captured by the surrounding phytoplankton. Of course, it works only if the shells, which become waste after consuming, are not incinerated, because in that case, all CO2 absorbed comes back to the atmosphere. Based on data present in literature, we have found that approximately the percentage of shell weight on the whole oyster is constant and represent about 63% of fresh weight. The CDT, that is the carbon dioxide total amount captured per kilogram of oyster, has been calculated, as you can see in this slide. That is 628 grams, corresponding to the weight of shell per kilograms of whole organism, multiplied for the percentage of calcium carbonate in shell and the relative mass content of CO2 in calcium carbonate. As a result, 1 kilograms of fresh oyster permanently stopped and removed from the sea when harvested about 300 grams of CO2. At this rate, based on the overall annual production of oyster in 2020, that means a sequestration capacity of about 1.7 million tons of CO2 and extending to the cumulative oyster production based on FAO data. Since 1950, approximately 35 million tons of CO2 have been sequestered. Of course, to this data, the amount of CO2 emitted as carbon footprint for production should be subtracted. Consider the average carbon footprint seen before, the balance would be maintained positive. For example, for China, we have seen before about 70 grams of CO2 emitted to produce 1 kilograms of oyster. That means a net sequestration capacity of about 200 grams per kilograms. Namely, that means that oyster can sequester permanently stopped 1/5 of their fresh weight. It is difficult so far to estimate precisely the net carbon capacity because of the several different farming systems worldwide, which deserve each a specific LCA analysis. Data are not available so far. To conclude, in an ecosystem perspective, and only in an ecosystem perspective, which takes into account the permanent storage of carbon in the shell, along with carbon footprint from all farming operation, oyster farming can be a net carbon sink. Results achieved configure oyster farming as a sustainable aquaculture practice and opens the discussion to the recognition of its carbon credits in a carbon market. Thank you very much for your kind attention.